and welcome back to Calculus 3 on this glorious Monday evening. Section 12.2, Graphs and Level Curves. Well, first we define the function, multivariable function, two variables. And if you remember the function definition that you learned in pre-calc and then reviewed in calc, it's going to be pretty much the same, except now we're going to have more than one independent input. What we are dealing with is multiple variables controlling a single output, which is how most of the stuff works. It is rarely one input controlling one output. If you think about, I don't know, car, you have to have all of these different things work together in order for you to go from point A to point B. Weather model, right? You have the air pressure and the temperature and whatever else to come up with one possible, right, solution, well, prediction. So when we are talking about these functions, in good old days, when we talked about 2D, we had that y was equal to f of x was input, y was output. We said function was a rule which took each x from the input into a unique y into output. I was mapping like that. So you have an input x which maps into a y. We had the domain, which is the set of all input values, and then the range, set of all output values. So, and we had the graph of a point right here, x, y, or we could have a line graph, right, for x squared or whatever else. So that was good old 2D. Now we're going a dimension higher. I'm going to take a look at z as a function of x and y. So what I have now is two variables, two independent variables will be making up z. I will give you a concrete example. 2x squared plus 3y is equal to z. So plug in a value for x, plug in a value for y, and you will compute value for z. We can write it in implicit form as f of x, y, z equals to 0. This one is later used in differential equations and so on. We are mainly dealing with this. And you have the example on the right. So definition of a function. Now this is something that might show up on the exam as state as is, no partial credit, 4 points, just like on Calc 1 exam. Function is a rule, so function z equals f of x, y is a rule which assigns to each ordered pair x, y in the domain a unique y, unique z in the range. So now the mapping looks like this. We have xy plane and a point xy somewhere, and then we have a z-axis, so that maps into some value z. Now, the domain could be the entire plane, xy, but it could be also restricted. Remember how I said always think of xy as the floor of the room you're sitting in? Well, if you look around, it's bounded. It's not infinite, right? We could imagine this floor to stretch infinitely in all possible directions. But then this floor is bounded in this case by the walls that we don't get to wander off. So now that we have this situation, we would like to do just the basic pre-calc stuff, which is find the domain. You have a certain function given. What is the domain? What are all the values that you can possibly put in? And expect the solution. So let's discuss a few of these cases. So find the domain of a function. First example, A. How about f of xy is equal to 3x squared plus 4y. You should be thinking the same way, just like you did in your basic pre-calc class. Is there any value that you can possibly think of that you wouldn't be able to plug in and get the answer? Think of positive numbers, negative numbers, right? Whole or rational, irrational, zero. Are there any numbers that we would have to exclude from set of x and set of y? And the answer is no, right? Real. Well, we're dealing only with real numbers. Well, even in complex, it was whole as well. So it seems as all x and y values are just fine in this case. We can plug in any number we can possibly think of in these. So we say x belongs to R, y belongs to R. So all real numbers for x, all real numbers for y, all of their combinations, everything is just fine. No issues there. All right, so all numbers. All right, let's take a look. Next one. How about element? So x is the element of R, meaning all of it. We can also say all of R squared, right? Double bar R squared. That's also notation for the entire plane that stretches infinitely in all directions. Cool. So how about the second one, please? Yes.
Well, y cannot be a negative that is less than x. X cannot be a negative that is, I don't say less than x, but if you were going to multiply by -1, it would be greater than the other number. So here cannot be, x plus y cannot be negative. That's what I'm trying to say.
Okay, great. X plus y cannot be negative. So we just write that in mathematical terms. That's an excellent answer. Let's just write it as a mathematical statement. You said it in English. Now let's write it. Domain. I have, and it's not a battery. Thank you. So x plus y cannot be negative. Right? That's how I write x plus y cannot be negative. This is the domain. This is the answer. Okay, f of xy equals to boo. What now? But where is x equals 0? Is that point? It's what? It's a line. Awesome. So what is this? Think of it as a whole plane as an input except the y-axis. You're not allowed to use any point on the y-axis because x is equal to 0 for every point on the y-axis. So r squared minus y-axis. So domain is all of the real numbers that you can, all ordered pairs that you can think of. Another notation would be Cartesian, like this, whatever. So it's the entire plane, x's and y's, except the y-axis. So that's why we take away minus, right? That's the negative. Minus. It's not a hyphen. So this says everything, and then take away all of the points that are on the y-axis. All right, let's see. What's the domain there?
Squared plus y squared is, no wait, so there's just a way of putting it back in? A little other than
Sam just did. Did you hear what he said?
greater than, no.
Yep. Every time you have a square root, you have to make sure that the argument of the square root is larger than 0. Otherwise, you'll get negative numbers under the square root, which guarantees complex values, right? So the first step is to write 9 minus x squared minus y squared needs to be larger than 0. Move x squared, 9 squared to the other side, so we have x squared minus y squared less equal than 9. So this is it. This is the answer right there. That's the answer. It's a circle and everything inside that circle. Let's do the crazy ones. So think about this one. No coughing. How's it going? All done? Yes. Okay. So it requires a little bit of analysis, right? It's not as simple as the previous case. Nice. So we have this plus 3x, but we know that that doesn't really do anything, right? We always worry about the restrictive part of the function. I always like to say, imagine if you are, trying to catch the train, which is slowly creeping out of the station, but the doors are still open, like in many other countries. So doors are still open, right? The train is slowly moving, and if you run, you can catch the train, but your grandma is with you and she's going on. Right? So now you're faced with a moral choice dilemma. Right? Train, grandma. Right? So when you're looking for, when you have multiple terms in a function, you always look for the restricted term. This one is all good. That's always polynomials would take any value. So technically all we need to worry about is x times y to be positive, right? And we don't want equal to 0 in this case. We don't want equal to 0. Now you could possibly graph this as well, right? Show the quadrants from which the points can give you. So x times y needs to be positive. This is positive x-axis, positive y-axis, so all of these are cool. And then second quadrant to the left, right, would be negative x times positive y. That would be negative, so that's not good. Then the third quadrant, we have negative times negative, which is positive. And then, again, the fourth quadrant is not good. So these are the two quadrants that you can actually pick values, points from as the input. And you would be able to come up with a real solution for this question. So that's that part. That's what we have. Definition of a function, 2D function, 3D function, so two-dimensional input, providing a one-dimensional output, which is obviously 3D, so x, y, z. And we have understanding that domain, we can find the domain with a little bit more analysis than what we are used to from before. The next part is to learn about these level curves. You need. So, what are the level curves? So, level curves are going to be cuts that are horizontal, right? So, think of the slices. You take paraboloid, you cut it, and you get all of these cross sections. So all of that is happening, in this case, on z-axis. So let's say this is 9 in terms of the height. These are 3s. We can write the equation of this. Look, what would be the equation of this? Let me see what you learned from the previous without flipping your notebook. X and Y is defined by a circle. Awesome. Three squared. Yes. So this is something that you will have to know to survive chapter 13. You see a shape like this, you should be able to immediately write x squared over 9 plus y squared over 9 is z. Over 9. All of them, yeah? Because it could be elliptical. If they're like 2 and 5, it will be 4 and 25. All right, so, yes?
You didn't mention in conic section last time. I forget how you find the sins of an ellipse.
Well, we don't deal with that in Calculus 3. All right, so we learned this shape last time as elliptical paraboloid. Elliptical because this doesn't have to be a circle, it could be ellipse. In which case, a squared and b squared would be different numbers. If it's a circle denoted by 3 and 3, then we know that x is equal to y, which means 3 squared 9, 3 squared 9. So we have x squared over 9 and y squared over 9. Now, y is equal to z. Well, it wraps around the z-axis. How many of you got the helix to wrap around the y-axis? Remember the exam? Helix was whatever it was, 2 or 3 cosine, and then comma t, and then comma sine, right? So it was wrapping around y because that single t was in the y spot. Well, here is that special thing that is happening here is around z. Z is not the one that is squared, so it's wrapping around z. Now, if this is wrapping around y, the cone, wrapping around the y, it would be z squared, and this would be y. So you want to kind of get that stuff while it's still fresh. All right?
So that 9 that you're giving us, that's on the z-axis, that's unnecessary. Do you want another explanation?
The 9? Nothing for 9 now.
That has nothing to do with formulation.
Yeah. We have completely ignored that. So this is x, and this would be x equals y squared over, let's say, 9 plus z squared over 9. And it's wrapping around z-axis. Sorry, x-axis.
So we keep going though, right?
Yeah.
You just tell it yourself, right?
Mm-hmm. So you see that whatever axis is wrapping around, that's the one that it's single. So now what are these level curves? Level curves would be these dotted lines if you cut at that elevation. So here, I say z equals to, I don't know, let's say 6. So level curve at z equals to 6. Level curve at z equals to 6. So what do I have there? Well, I will have x squared over 9 plus y squared over 9 is equal to 6. Which is x squared plus y squared equals to 3 root 6. So what is it? It is the circle, because that's the trace that you get when you cut. See, take an object, think of this object as your paraboloid, and then at 6 inches height, take a sword and just cut straight through. What are you going to get? This line that outlines the object would be this line here, which is mathematically this equation here. This is how we tie physical reality with these equations that we write. So the physical object that you see, let's say this one, again, you cut at a 6-inch straight, because every time when we're doing the level curves, you're cutting with a plane z equals 6. Plane z equals 6 is always parallel to the floor on which the object stands. So now, if I cut through at 6 inches, the resulting equation is this circle, in this case, right? If it was ellipse, it would be ellipse, and whatever it is. So the shape will tell us. And cutting is done very easily. All you do is plug in 6. That's it. Come on. Because it's the radius, r squared on this side will be 9, 6 times 9, right? Yeah. Square root of 9 is, oh, I forgot to put the square. Okay, I see what you, yeah, I was supposed to put the square. I wanted to show the radius. I could have put 54 and just be done with it. You can put 54 instead. You can. Okay. You can put 54, yes. You can put 54. The reason why I'm putting this 3 root 6 is because I want to show the radius. So let me just draw that radius. I'll do this. I'll draw the radius here. 3 root 6. Joe. It is. Level curves are always plane curves that you obtain when you cut to the parallel. Traces to cut any way you want. This is fixed. It has to be z equals a value. And it always cuts parallel to xy plane. So you can only get slices this way. And yes, it is a trace. But this is a very specific one. Huge application of something like this would be maps. So if you ever see topological maps, you have all of these busy lines. These busy lines are level curves. So think about it. You have a hill, and you slice through the hill, slice through the mountain, and that outlining contour shows. So every time when they are far apart, that's, very kind of flat. And any time, right, it becomes steeper. This is very steep. It's insanely steep over here. So, for instance, military reads these maps, right? Easy. The guys are trained because you don't drive roads, right? You drive off road. And you see from the map, there's no way you can drive here. That's really steep. Okay, these level curves are really close. So I will show another image. These 3D images are very easy to understand when they're drawn nicely. So you see the cuts you see your xy plane, that's the floor, the gray one. And then z equals a number is the plane which cuts. And that plane is always parallel to the floor. So we have two planes over here, the blue and the orange, whatever how the color is. And z equals z0, z equals z1. We are cutting this shape, right? It's like a sand pile. And here's what you get as level curves. So you see it's a kind of steady climb. And these are, like, they are spatially kind of equally placed here. Then these guys, like, are spatially. Now let's that's steeper, and you see how many more of those circles have. Where are the termites? There they are. Termite nest, right? Or whatever the hell this is. You can see over here where there is no much of a slope to drive up. You see how they're far apart. And then for these guys that are very steep, see how they come together. That the reason is, as you go and cut it, 1, 2, 3, 4, 5, 6, 7, right? When you cut it 1 and 2, and these guys are far apart, that means there was not much change in terms of the vertical height. Lines are far apart. As soon as you're getting clusters like this, that means it's very steep. So now, hopefully, when you understand this, you go back to that map, which unfortunately I can't enlarge, and then you say, hell no, there's no driving this way, because it's just going crazy. Yes?
Is that kind of a derivative for the three-dimensional?
No, but yeah, no, it's not.
Okay.
Is there like a slice, a little slice that you're talking about?
They're not slices, they're actually traces of what you get when you cut it off. And I'm regretting not having an apple here with a knife because A, I'm hungry, and B, you would be with the. But then, yeah.
That's fine. That's why you know the apple.
Yeah.
No, you watch it.
And what is A and B, if you pay attention.
Well, you like peanut butter on your apples?
I've got an apple if you feel it.
I have peanut butter.
Wow. She's like, wait,
I'm not gonna hear like 5 topics for lunch.
Yeah. I actually really wanted to bring, first time teaching calculus, the watermelon and the sword, and the school said no for the sword. Anyway, your delivery is here. So, say hi.
What's that?
John, he took care of this class a long time ago, and now he's in charge. Bring her.
How much guys I like to think of?
All right, so closely spaced contours, rapid changes in elevation, widely spaced contours, slow changes in elevation. So when next time you pick up a map and you see these contours, you will be able immediately to tell what kind of terrain is there.
You actually
Clearly,
read the map.
yes.
You do?
Yeah. That's fun. Okay. How do we get them? As I said, you set z equals to 0, z equals to 1, z equals to 2, z equals to 3, and you keep computing and getting different values. So you see that gray shape, right? Gray shape is just a piece of lead paper bent, that's all it is. The grating, but it's at the angle, so it looks like this, right? And now, as you cut with these lines which are parallel, so as you cut like this, the trace that you get is a parabola. Let's put that together. So you see the green ones are parabolas. When you put z equals to something, a number, like z equals to 0, then one goes, these two guys go to the other side, it becomes x squared plus 1. So y equals x squared plus 1 is the parabola. Right? So you can see what the contours are. We see that if you approach this way, there's not as much steepness as if you go sideways. How does that transfer here? Well, if you go this way on top, right, of the shape, it will be much easier to drive up. Right? This way, it's cool. This way, not so cool. Well, Spider-Man can go for it. That's how it goes. Applications, plug numbers in. And
So when we were doing like x squared plus y squared equals like some number, I think you said this already, but that's a bit of a level curve for a sphere.
level curves of sphere will all be circles, right?
Yeah.
X squared plus y squared. And how would they look like? They will start from a point and then expand till the sphere is the fattest, and then it's going to go contract again into a point. So it starts at a point, extends, and then goes back. Because as you cut the sphere that way, that's what you get. This is a cool chart to kind of see the progression. So explicit form, implicit form. So y equals f of x, I already talked about it briefly. X is the input, y is the output. It's a 2D world, xy plane. You just get to graph whatever, sin x or whatever. Now we have two independent variables, z equals, this is what we covered today and defined it today, xy, so two independent variables are governing z. The point would be xyz in a 3D implicit form, and then R3, so you are graphing this in a 3D, making a 3D printer. Three independent variables producing a fourth dependent variable, again, same progression here, R4, and then you can have in any dimension. So string theory uses 11 dimensions. So we have, in mathematics, very easy. You can have whatever dimensional space you want. It's just the number of variables. And if you're going over 26, right, just start using other alphabets or just switch to x1, x2, x3, and then, you know. So like over there, they have x to the n. Cool. That's that. We are going to restart the stream for the next. Okay, let me just see. Restart